Okay, so welcome back to the seminar. So our second speaker today is Venier Chesov, and he's going to talk about.
I'm going to talk. My talk on the continuation of Kenta's talk in some sense. So Kenta's talk was advertisement of our book, and I will try to advertise problems which we didn't solve. We actually really want to solve Calabi problem for Fanas Riffles, but we didn't finish for all of them. We finished for general members. So basically, if you look at this, of this problem for Fanas Riffles. So yes, okay, here maybe smooth. So the first step, to solve the problem for general member of each family, solve this case stability problem for general member of every deformation family. This is done. The second step is basically to do the same every member, every smooth member. This is not done for 19 families. But we know at least conjectural answer, what answer should be. Yeah. And suppose this is done, we want to, the next final step, this is like a final 1, 2, 3, find all singular k-polystable limits of smooth Fanas Riffles. So basically, it means describe this, describe reducible components of the modular space, which contains the corresponding families, smooth Fanas Riffles. Yeah. Okay. So once this is all done, problem going to be completely solved. Okay, well, theoretically, you can go further. You can describe the stack structure of this, but this is maybe too difficult. Okay, so this is done. This, I believe, it's going to be done at some nearest future. Very powerful technique is a Aban-Zhuang method, but in some cases, it doesn't work well. But I think maybe we just need a little bit new ideas. But this step is almost not done. So let me just briefly mention what is done at this step. So because we're a little bit stuck here, we already started working on this. Okay. And even in some cases, even because we know conjectural answer here. So we can work on this because more or less conjecturally we know what we get here at some point, maybe later. Okay, so what is known here? What is known about the modular? Let me just basically briefly mention. So first of all, let me remind, we have 105 families. Yes, and all of them are irreducible, unirational. You mean the parameter spaces, Yes, so in 27 cases, no k-polystable members. 78 there exist k-polystable members. And in 20 out of them, in 20 families, such member is only one. just contain one member. For example, P3 or quadric in P4. Yeah, just one member. Okay, so in this case, this problem solved. You just have a point. Moduli space is just a point, so it's very nice. So in 58 families, we have really moduli parameters. Please, we have moduli, and we have very few results. So, for example, what we know. This is just the continuation of Kento talk, and finally I will describe what we're doing right now about this family which described in the abstract. So let me just give a few examples. So for example, you have cubic threefolds in P4, and they K polystable if and only if corresponding point JIT is stable for the action of SL5. And this is Yu-Chin Liu and Qin-Yang Xu. Yeah. Okay, so this is relatively recently, but this is not easy theorem. Just one family, complete answer, and JIT stability for cubics known. So if you just get explicit information about how singular they can be, and all smooth, of course, K-stable. Maybe more complicated example, you take quartic and P11112. This is sometimes called quartic double solid. Why it's called like this? Because if you project to the first 4 coordinates, this is going to be double cover ramified in a quartic surface. So in this case, stability is more or less K polystability is equivalent to K polystability of a pair P3 and this quartic surface. Okay, and K moduli, in this case, recently described by Kenny Asher from Irvine, Christine de Vleming, and Yu-Chin Liu. Yeah, but in this case, this is not just JIT. It's more complicated than this. You can take quartic surfaces, and you can consider like a moduli, JIT moduli space for quartic surfaces with respect to the action of SL4. But if you look at this case, you see that there's an issue, because if you can take a quadric surface, multiply by 2, non-reduced quartic. So basically, quartic surface which is not reduced, just a quadric surface like 2 quadric, where this is a quadric surface in P3. And it's JIT stable, but the corresponding double cover, it's reducible. So it cannot be K polystable. So you have to blow up this point. So you blow up this point, the point which corresponds to double quadric. But then you have to contract a curve of which correspond to some quartics which are quite singular. So and then so this is a blow up blow up this point, and then you contract some curve. And then you get a component of a moduli, and it's even semi-normalization. So basically, up to semi-normalization, you get this moduli space for this. To be precise, this is the semi-normalization of this guy. Oh, okay. So even this example show you that you just use JIT and you're done. This example show you that JIT is not enough. You have to blow up and then even contract something. And another maybe example here is not example, this is non-example. So if you take a quartic in P4, we don't know. There's a recent paper of me, Hamid Aban, Alkas Perchik, Yuchen Liu, and Andrea Petrache. Basically, we investigated this moduli. Essentially, our main result that we don't know how moduli looks like. There was some candidate for the model. We show it's not the case. So this is completely unknown. So yeah, but all these cases, it's when number of parameters are big. So this case, number of parameters are 0, easy. In this case, difficult, number of parameters are large. So probably one way of approaching this problem is to consider low dimensional cases. Cases when number of parameters are not so big. And in this case, maybe the structure of moduli is not so difficult to describe. So let me give one example. So what is the first step after 0 dimensional case? It's one-dimensional case. Yeah, we consider one-dimensional case when moduli should be one-dimensional. Let's consider basically one-dimensional components, just to see how things works. Components of this. Okay, and we have actually six such families. And we already know that the answer should be up to normalization P1. So basically, up to normalization, it should be P1, but in every case, it's going to be exactly P1. It's going to be smooth. And we, in each of these cases, I will maybe present few, we know case stability for all smooth members. Okay, let me just give you one example. Just example from the book. It's actually in the introduction to the book. It's very, very nice. This is family 224, which is, it's a divisor of degree 1, 2 in P2 cross P2. It's very nice family. And using basic linear algebra, you can show that if this is smooth, it can be given by this equation, xu square plus yv square plus zw square equal lambda xvw plus yuw plus zuv. I didn't finish the sentence, but before I finish the sentence, observe that this is basically S3 action. If you permute this coordinate, if you permute this coordinate, this equation is symmetric. So you can get either this equation or equation without this term or equation without that to this terms. So basically either this, or if I just erase this, just this, no lambda, nothing, just one threefold, or another threefold. But both of this, in both of these cases, they either trivially degenerate to the case when lambda is 0. So in some sense, we don't need to consider them, because for every lambda, this guy is K polystable. And this is proved in the book for every lambda, including singular cases. So in a singular, when lambda cube is 1 or infinity, you get a singular threefold with 3 singular points, ordinary double points, but all of them isomorphic. This is lambda is a parameter space. It's not a moduli, but basically this immediately implies that the moduli is P1, and this is complete solution. This shows you the singular limits. Without, so this is 1 point in the moduli. So even if you solve the problem for smooth members, you know that basically you have P1 without a point. You just need to find the singular limit, only just one k-stable degeneration of this. But it's given by, you make it singular in this way, and the same proof works. Proof essentially almost the same in singular case. There's small difference here. Okay, and here the answer coincides with the GIT picture for the SL2 times SL2. Okay, so here's no surprises, yeah. And okay, so let me consider maybe another example, not from the book. It's family 222. You have a blow up of P3 in a quartic rational curve. Okay, how to approach this case? I mean, this is a description of the smooth members. This is blow up. But from elementary projective geometry, we know that this curve is contained in the unique quadric. Yeah. And this curve is a divisor of degree 1, 3 here. Okay, so basically here, K polystability coincides with the GIT stability for this curve in P1 cross P1 of degree 1, 3 for the action of SL2 times SL2. And again, how to prove this? This is just post factum. You can represent this curve in basically in the following equation: ux, if this is coordinate u v, and if this is x y, you can show you this curve can be given, if it's smooth, by this equation. And like in this case, you see that in this case, you have an action of the group Z2 times Z2. And if you remember, in the one of the various slides of Kenta described valuation criterion, and he basically mentioned that this K Zikwan-Zhuang result that K polystability follows that if you have for every prime divisor f over x, which is G invariant, you have beta of G bigger than 0. In our case of threefolds, if you look for this divisor G, f, you look for this divisor f, again, what its divisor over x. You look for the center of this divisor on x, and you have three possibilities. It's either surface, It can be either curve or a point. But surface case, it's all done. Beta invariant of all surfaces in every smooth Fano threefold computed by Kent in his paper and estimated. And if F is a surface, we know in each of these families, we know that beta is positive. Curve case is more difficult, and point case is the most difficult. But if your divisor is G invariant, for example, in this case and in this case, these groups do not fix points on the variety. So this means that this case is impossible. We don't need to consider this. To prove K polystability, in this case and in that case, we only have to consider this case. And this is much simpler than that. More difficult than this, but much simpler than this. So this is, in every case, this is the most difficult case. So if you have any symmetry, which doesn't fix a point on your variety, this helps a lot, just dramatically. And by some surprise, in this case, this is exactly every K polystable case. If I erase this term, I break the symmetry, and my threefold becomes not K polystable. And so here, all of them are, yeah. Interesting case, interesting remark. If you look for this Z2 times Z2 action here, you may say, actually, it may fix a point for some values of lambda. But this is exactly values of lambda when this is not K polystable. Yeah. So okay. Good. So to be precise, when lambda is plus minus 3, this group fix a point. Yeah. But this case either trivially degenerate to the case lambda is equal to 0. So in the modular, it's the same point. And you can think what are degeneration. For example, degeneration is when lambda is infinity. In this case, this quartic curve degenerate to a conic in 2 lines. Yeah, and your group just permutes them. Yeah, so, okay. So very similar situation actually happened in many other cases. In this, yeah, but one family is a bit special. So let me mention this because it's actually very nice, and let's actually show you the difficulty which may exist. Yeah. Yeah. So in low dimensional case, usually problem is not so difficult because you already know your answer is P1, and problem is solved for smooth members, and you only need to find 1 or 2 singular limits, which is not so, you don't need to blow up anything. So life is not so bad. Not like in these cases. Okay. So let me just mention one family. It's just one dimensional. Then I go to main topic. So one case, 313. It's also one dimensional modular, and but this example shows that life can be more difficult than here. Okay, so what is this? X is a complete intersection of 3 divisors of degree 110, 101, and 011 in P2 times P2 times P2. And let's choose coordinate x0, x1, x2, y0, y1, y2. Z0, Z1, Z2. So this is actually a very nice linear algebra exercise for year 1 students. You will see in a second. So what this equation means, if you called this point x, this is y, this is z, it basically means that this is a system of equations, x transpose m1y equal to 0, y transpose m2z equal to 0, x transpose m3z equal to 0. Yeah, where mi 3 by 3 matrices. So suppose you want to describe moduli, k-moduli of this threefolds, what should we do? So if there's many ways how you can do. So one possible way, you take this complete intersection and you just apply GIT for SL3 times SL3 times SL3. Yeah? But and also add symmetric group action. But it's very difficult. At least I don't know how to do this. Yeah, it's possible, but it's not very clear what you get. But maybe we can just play around, like in this case. Of course, you can do GIT, solve GIT problem, but finding this normal form is much simpler than GIT. This is basically linear algebra. And here, this is also linear algebra. So in this case, also life is difficult, but life is more difficult than this. But the difference between this case and this case, that here, even if you don't want to find nice equation, if you just want to solve GIT problem, it gives you the right answer. But in this case, if you just do usual GIT, you don't get a nice answer. And then there's a reason I will explain in a second. So first, let's try to simplify this. Any suggestion how we can simplify it? No, we can change coordinates. Like a hint, if x is smooth, determinant of this is not 0. All of them, determinant of each matrix is not 0. So for example, instead of y, we can have, this is going to be your new y. Yeah, and then you may assume m1 is 1. And then you can do this, your new z. So basically, you may immediately m1 equal to identity, m2 equal identity. So life becomes simpler. Yeah, so we just erase. And now what to do? Now we can change y and x, y, and z in such a way that we keep these two equations. We change this, but essentially this means that we're going to change m3 as m3 goes to some a transpose m3a, where a is a linear change of y or z. This is going to keep you these two equations, and you change this. And this is, if you give it to every undergrad tells you, sure, we can make this identity. Because we know it's quadratic form. Yeah. The only problem that M3 is maybe not symmetric. If M3 is symmetric, you can make it identity, and you get nice threefold. It's very special. Its automorphism group is PGL2, their product with S3, and problem solved. But in general, it's not symmetric. So then you split M3 as a symmetric part, symmetric, and a skew-symmetric. Yeah. And then you can make, changing coordinates further, you can make this to be identity. And then you start simplifying this already using orthogonal group, or like PGL2. But somehow we didn't decide to make it identity. Instead of identity, we make it to be 0, 1, 0, 1, 0, 0, 0, 0, minus 2. It's basically the question which conic you like the most. You have two conics, x squared plus y squared plus z squared equal to 0. It's one nice conic. And another one, xy minus z squared equal to 0. So we prefer to use this. It's essentially the same. So, and basically this means that now you can use matrices which preserve this conic and simplify this. And the answer is, so up to action of PGL2, this can be given by two forms. Either this matrix, basically you ask what is the most simple skew symmetric matrix we could get in this case. And the answer is this. Either you get skew symmetric matrix lambda minus lambda and all others are 0, or 0, 1, 1, 0, 0, 1, 0, minus 1, 0. Yeah. Basically, this is classification. You can change coordinate in such a way that this is 1, 1, and this matrix either that or that. And lambda is your parameter. But this is a bad case. In this case, connected component of automorphism group is additive group, so it's not reductive. It's smooth. In this case, 1 minus 1. It's like 0, 1 minus 1. So basically, for skew symmetric, you may assume all entries except 2 are 0. Yeah, and you either can put it into this place or that place. Yes, and in this case, connected component of automorphism group is C star, GM. And all of them are k-stable. K-polystable. Okay, k-polystable. If smooth. But there are two parameters. Lambda is plus minus 1, and lambda is infinity. Okay. It's easy to see that in the parameter space, this is 1 point. Because if you swap lambda to minus lambda, you get isomorphic threefold. So basically, using this, and of course, okay, using this, you see that your moduli should be P1 without two, like we already described our moduli, P1 without 2 points. Lambda is plus minus 1, and lambda is infinity. Yeah, but if you just substitute lambda to be plus minus 1 or infinity, you get unstable threefold. Why? Because this parameterization is bad. If you look here, we have a symmetry group acting. It's independent on the parameter. The action of this group doesn't use parameter. So when you can put parameter to the limit, your group survive. It's still here, and the same as in this case. But in this case, if you just look, what's the automorphism group of this threefold? As I already said, you have connected component, GM, and it's very easy. It has additional involution, which swap basically X and Z. You can swap X and Z and change some coordinates here. But so you, in this picture, you immediately see one involution. But this is simply because we broke the symmetry in the beginning. So you can do the same trick with any other coordinates. So resulting group going to be S3. But this action of S3, unfortunately, in this parameterization, going to depend on lambda, on your parameter. So when you put lambda to be infinity, some automorphism disappear. So your limit is kind of not nice. So you can find a different parameterization, S3 symmetric, very similar to this one. It's possible. And then you see that this, in the new parameterization, this point is going to correspond to K-polystable toric threefold, which is given by a very simple equation, which probably I don't, yeah, maybe I write, okay, it doesn't matter, I'm not write it down. So it's very simple equation and different parameterization. But this point still gonna give you the bad equation. You put, it's actually even worse. In this new parameterization, when you put lambda to be infinity, the corresponding point not gonna give you threefold, it's gonna give you fourfold. And then we spent quite a lot of time on, there was a group project with Hamid Aban, Anna Sofia Kalageras, Jesus Martinez Garcia, and 4 our PhD students. It's supposed to be exercise research project for PhD student. And basically most of the project we spent on looking the limit here. What is the limit here? It's just 1 point, yeah. And answer was that we were looking in the kind of wrong representation of this guy. This is complete intersection. But for example, your co-author, Zhenya Schindler, he studied what's called maximally non-factorial Fano threefolds. And there's a nice phenomenon which basically, if you consider very simple singular limits of these guys, they're not necessarily complete intersection. So they, even if I assume, for example, that I look for the limits of this threefold with ordinary double singularities, with the simplest possible singularities, very like one ordinary double point. And it may be complete intersection, but in this case we found it, but it was also has not reductive automorphism group. But there is another one, and there's another one. Surprisingly, it has it's a Pfaffian. It's a dimension 3 subscheme, but it's not complete intersection. All of them can be written in the Pfaffian equation, but singular one, not complete intersection, yeah. And surprisingly, geometrically, it's very simple to describe. Actually, here, I don't know, maybe this is kind of coincidence. There's coincidence how you can construct singular limits of this one. For example, you take a quadric in P4, and you pick 3 points on a quadric. Any, in general position. Okay, and then you blow them up. You blow up quadric and these 3 points. And then you have unique plane containing 3 points. This plane intersects your quadric by a conic. You take this conic here, and it's intersect canonical divisor by 0. So you contract it. And you get this point. If you just think about this, you take a quadric, you have 3 points. If you have 3 points, 3 points determine your 3 pair of lines. You can project from the lines. Projection from the lines gives you the map to P2. You have 3 maps to P2. When you blow up these 3 points, you get a morphism, but this morphism contracts this conic. So you get, it's a unique threefold. It's very easy to find equation here. And you see equation is not complete intersection. It's a Pfaffian, given by Pfaffian equations. So, and once you observe this, you don't even need to prove that this guy is polystable, because the proof implicitly contained in our book. Why? Because actually, if you blow up this conic further, you get Fana. This is not Fana. This curve intersects trivially with canonical divisor. But if you blow it up, it's a Fana. And we prove in the book that it's K-polystable. And this proof, if you just look for the proof, it immediately implies that this K-polystable. Proof, it's absolutely the same proof. You just play around a little bit. Everything is, so in some sense, it just follows from the book. Yes, and you get this guy. So what I want to say that even if you have nice representation of a threefold, and you see, okay, natural GIT problem is just this. It may be not the right GIT problem and doesn't give you the answer. Maybe to get the right GIT problem, you need to do something else. Okay, so finally, main part of my talk, there's divisors of degree 1, 1, 1 in P1 cross P1 cross P1. Today, maybe yesterday, with Kenta, we decided to change the title of our paper. So our we were writing a paper with Anna Sofia-Kalogeris, Maxim Fedorchuk from Boston, and our original paper, a title called K-stability of Fana threefolds of degree 24 and Picard rank 4. But we found some papers of physicists who studied the same thing, but they called them 4 qubits. Kenta, did I spell it correctly? Maybe qubits like this, yeah? Quantum bits, qubits. So K-stability of 4 qubits. Of 4 qubits. So this is a physics name for divisors of degree 1, 1, 1, 1, and P1 cross P1 cross P1 cross P1. And when you look at this, you immediately say, okay, we just have to do GIT. For which group? SL2 to the power 4. Yeah, and also semi-direct with S4. Permutation of coordinates. Yeah. So we computed. So first of all, before GIT, there was a theorem, I think it's a couple of years ago already, maybe last year, Belousov, Loginov, which basically said that if X is smooth, then X is K-stable. And basically the proof was just Abanjuan theorem. And formulas found by Kenta in the book. From the book. So Kenta described Abanjuan theorem and how to state it. But when you want to actually apply it and to compute all these barycenters, it's quite long process. But Kenta found very simple user-friendly formula how to do this. And once you basically use these formulas, it becomes exercise. So they apply, but if you look at this threefold and you ask which flag you want to choose. So basically flag is like a, say, point, your initial point P, curve, surface. Point is fixed. We want to estimate here delta P. you need to find the surface. Once you find the surface, it's the next. Yeah. So any suggestion for a surface? You fix a point here. Which surface would you choose? Just look at this. You need this surface here, which passes through given point. And if you remember what Kenta mentioned, you need barycenter to be close to 0. So it basically means you want your surface to be like not very big. Surface has to be small. Just look at this. There are many choices, but one which may immediately, you just, we have X, we have 4 copies of P1s, and you can project to P1. If you project to P1, any of them, this is a fibration on Delpezzi surface of degree 6. This is basically fibration into Delpezzi surface of degree 6. Yeah. So you can take the fiber which passed through the point P. And this is, yeah, but when you choose this surface to be fiber of this projection, you may accidentally choose the singular one. And if it's singular one, usually theory becomes difficult. I mean, doesn't give you nice estimate, but you have 4 of them. Okay, so basically these guys check that one of them always smooth. And then the rest becomes just an exercise. So, okay. So, but now, if we want to describe the moduli, the one option, you can just apply GIT. So when we started this project, it was actually on a conference in September in Oxford, Clay conference. And we was absolutely sure that answer is GIT. It's going to be, you take a GIT moduli, and this should be K moduli. And one way how to prove this, if you compute this GIT moduli, we already know, okay, it's sort of clear that the smooth one going to be GIT stable. So it means you should have a rational map from here to this K polystable moduli. But if you sort of prove that this is a morphism, what does it mean? It means if every element here is K polystable, it's a morphism, then this has to be like semi-normalization. It's because it's an open part, it's 1-to-1. So it has to be, so basically it's either isomorphism, or if you also know singularity, if you show that deformation non-abstracts, that this is basically isomorphism. So if you prove that all elements here are K polystable, but to do this, you need first describe them. And when Kenta described them, basically hold GIT, but then we've Kenta found the physics paper where they did the same thing before us. Okay, and this is we didn't know. Okay, so anyway, let me. Yeah. Oh, but because what you have a point here. Oh, on the open part, you know that smooth member is K polystable, so this basically goes to the same threefold. So on the open part, you have a map, but it's not a morphism; it's maybe a rational map. But if you prove all of them are K polystable, but in order to prove that all of them are K polystable, you need first to find them, which is purely a GIT problem. But it was solved by physicists, which basically explicitly found the invariant ring for this quotient. And they why? For physics. No, physicists was interested in some quantum information. Physicists was interested in different problem. They just found the invariant. So basically, let's just do this. So space of such threefold is P15. And when you take a quotient by this PGL2 to the fourth semi-direct with S4. Okay, no, let's just first do by PGL4. They proved that this is isomorphic to P1, 2, 2, 3. And they found invariant ring. They proved this. And then when you, okay, let me say a few words. Yeah. So when so they found this before writing down the next quotient. What actually happened? What actually happened when in the beginning of the project we never thought about using any symmetry here. Why? Because we thought moduli is big, three-dimensional. So we thought general member should have no symmetries. We was absolutely sure about this. So unlike other problems, when we have symmetries, here we didn't find. But then on the same conference, there was a Carolina, no, she wasn't. Or she was. Carolina was? No. But anyway, we spoke with Carolina Rausha from IMPA, and she told us that she also studied this threefold, but from absolutely different point of view, like moduli of parabolic vector bundles on elliptic curve. It's absolutely different project, not related. And we chat with Carolina, and Carolina said, oh, I think, yeah, she said, you know, all these threefolds has quite a lot of symmetries. I asked her, how do you know? She said, oh, from moduli space of parabolic vector bundles, it's clear. You have some change of coordinate. And then we look here, and we said, so we checked how the group S4 acts here. And surprisingly, group S4 acts here with a kernel. Its action here is S3, and the kernel Z2 times Z2. So it means every member has this group of symmetries at least. So for all of these groups are the same. So basically, if you wish, you can just, this group is just, you fix group which just permute these coordinates. Yeah. And then, instead of going through the whole space of parameters here, all divisors of 1, 1, 1, you only need to consider divisors invariant with respect to this group to have the slice. But this is much smaller group. You make a much smaller space. This is P7. P7 is basically subset, linear subspace here, consistent of divisors invariant with respect to this. But now you look what the stabilizer of this space here. But what stabilizer? It means your group permutes, like a Klein group, permutes these factors. So stabilizer is PGL2. All coordinates are the same. So now you have to take a quotient by PGL2. But if you look at this of this guy, it's easy to see which representation of this group here we have. So sorry, not P7, P6. But as a representation is 7-dimensional space, and it splits as 4-dimensional and plus 3 trivial representations. 3 trivial representation of SL2, and this is 4-dimensional. But what is 4-dimensional? Representation of PGL2, SL2. This is actually symmetric 4th power of 2-dimensional standard representation of this group. But it's very classical exercise in plain geometry for kids to say that if you have this representation, stabilizer of general point is Z2 times Z2. It's, if you just think about this, you have a P1 and you have, what is this? This is 4 points on P1, binary quartics. And you ask this set, what's the stabilizer of this set in PGL2? Generically, is Z2 times Z2. Why? I mean, you take a circle on a plane and you take 4 points, you take a point and you project, this gives you involution. And then you do the same here. It's classical fact from plane geometry. 4 points on a circle give you clean group. So what does it mean? It means that general member of general element here, it actually has not just this automorphism group, it's Z2 to the power of 4. It's huge. I mean, like, it's a small group, but it's very big. And you can choose any action on this group. For example, you can choose action of this group swap coordinates, and action of the remaining 2 factors basically just swap coordinates on each and multiply by -1. And this gives you the very simple normal form for the equations, which is essentially P3. And this helps a lot. So, yeah. So basically we have, so if you have this coordinate, say x1, y1, x2, y2, x3, y3, x4, y4. So then the normal form for x, at least for smooth one, going to be a x1, x2, x3, x4 plus y1, y2, y3, y4 plus b x1, x2, y3, y4 plus x3, x4, y1, y1, y2. Very, very simple one. x2, x4, y1, y3, and d x1, x4, y2, y3 plus x2, x3, y1, y4 equal to 0. So you have this P4 with A, B, C, D. Yeah, and then this gives you this quotient. So we already know, so if you take a quotient by S4, then physicists also computed this, and this it was projective space with weights 1, 3, 4, 6, and the corresponding invariants they called how they called HR. This is correspondent invariance HRST. Yeah, and this gives you the slice of this map to P1, 3, 4, 6. And this is actually the quotient by the group WF4 with the kernel Z2. So this is a group of order 500 something, 576. So basically our model is a weighted, GIT model, a weighted projective space. We have very explicit equation. General member has a symmetry Z2 to the power of 4, and we can use either this as coordinates or this as coordinates as its invariant. So now we can, only thing we need is just to describe singular members. Singular members. So, and in short, everything almost okay. So we have singular member, general member is smooth. Smooth. Singular. General member has 2 A1 singularities, ordinary double point. Then special member has, this is a divisor of singularities, curve of singularities with 4 A1 singular points, one, so this is a curve, this is surface. Here, everything is given explicitly in coordinates with equation, everything like very, very explicit. Then 6 A1 singularities, 1 point, which correspond to the toric one, the point 1, 0, 0, 0. This is just a toric threefold, and it's k-polystable for sure. Then we have threefold with a curve of singularities, also 1 point. One curve. Curve singularities, yeah. So it's a curve. It's curve in parameter space. So far so good. Nice, very nice. Here we don't even need to prove anything. It's toric. Its barycenter is 0. We check it. Yeah. Nice. One thing is not nice, and you have a reducible one. Reducible, when basically divisor split as 1, 1, 0, 0 plus 0, 0, 1, 1. So it's very easy using the, first of all, using the symmetry we have. Theorem of Belousov and Loginov becomes basically half-page proof. It's very, very simple. Using the same symmetries, you prove this is k-polystable, 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 bad. So what does it mean? It means that this is our GIT moduli. We have a rational map to the k-polystable moduli, but it's undefined in this point. And what we basically proved, we proved that this is this morphism is basically weighted blow-up of a smooth point here with weights 1, 3, 2. Yeah, but if I didn't put it into in the abstract, I encourage you to guess what could be the degeneration. So basically, look, we have other degenerations of these guys which are not divisors of degree 1, 1, 1. We need to consider another model. Basically, we just guessed this model. We didn't have any particular reason. Yeah, no? Or we did? Any suggestion? What would be any degeneration you have in mind for this guy, which could be image of the blow-up of this point? Some limits of this, some nice limits of these threefolds, but which are not divisors here. It's just a natural guess, just suggestion. Just look at this. Well, okay, if it's not divisor here, it means we have to degenerate this. There's no choice. Any suggestion how we can nicely degenerate this product? Just a guess. Just a guess. Yes, this is the only thing that came to mind. There are a lot of degeneration, but one is very nice. But psychologically, it's difficult. I can explain why. Because we really like this. And this is we have here this symmetry. Yeah. So in some sense, when you degenerate, say, this and that, also, it means you a little bit break in the symmetry. A little bit. If you just think about this, yeah. A little bit break in the symmetry. So from this point of view, we was not very happy. It was counterintuitive. But you're absolutely right. So what you can do, you can break the symmetry like this. You can degenerate this two to P112 quadric cone, and this is to P112 quadric cone, and this is just a product. Yeah. And here you have a divisor of degree 2, 2. These are limits of this. You just degenerate this as to quad, just a usual. This is a quadric in P3, and this is a cone. Yeah. And for them, But of course, you have other symmetries which you can use. And for them, we found also normal forms. If you have these coordinates S1, T1, W1, S2, T2, W2, that normal form going to be this. Okay, let me just, in short, W1, W2 equal polynomial of degree 2, 2 in S1, T1, W1, S2, T2. And you can actually immediately see reparametrizing that these guys are actually image of blow up of this map with weights 1, 2, 3. But if you look at this is divisors of degree 2, 2 in P1 cross P1 in some sense. What Kenton mentioned in the very last page of his talk, our product, our theorem about K-moduli of some other families. And at some point, he also mentioned this modulus 1, 2, 3. So this was exactly moduli of curves of degree 2, 2 in P1 cross P1. So which is given by this equation, yeah. And here, in this case, you can also have a toric one. There exists one toric guy, toric member here. Which basically given by this product S1, S2, T1, T2. This product of this coordinate equal this. It's a toric. And you can also check its barycenter at 0. So we got extra okay, so basically what we proved that moduli, K-moduli, is just a blow up of this guy in one point. Exceptional divisor is P1, 2, 3. We almost proved this work in progress. I guess more or less proved, but we need to check details. Yes, and this is basically give you this moduli of these divisors here. Yeah. Okay, so more or less this is it. So it shows you that in general life is kind of more complicated. K-moduli is more complicated than usual GIT moduli. And for example, we found these divisors, I mean, these limits, in some sense by guessing. So we didn't have any kind of any algorithm how to do this. We just thought and it worked. So yeah. Okay, this is it. Yeah.
So any questions?
Delpetsa will know everything. I mean, smooth one. It's a paper of Hadakas Potisan, and basically K-moduli described explicitly. Just in each case. Yeah, in each case. So absolutely explicitly. For cubics, it's GIT. For Delpets of degree 4, this is basically P1. For degree 2, it's a GIT of the plane curve, I think also blown up. Not blown up. I don't remember actually. So basically, it's all described in this paper very explicitly. So yeah, it's actually they did this before all of this technique was available. So now you can do it much simpler. Yeah, because with this type of result and with recent result, this is now can be basically rewritten in a couple pages. It should not be difficult. Yeah.
So basically, again, we have a moving step from GIT to K-stable instead of the other way around.
Other way around. So actually, yeah, usually, for example, okay, I already erased for the cubic threefolds. The idea was the opposite. You first take abstract K polystable limit, you try to use basic properties of K polystable threefolds to show that K polystable limits also has to be cubics. And if you prove this, you have an opposite map from, say, here to here. And then you use a GIT. But in our case, it's very difficult. So it's, and it's not true. So because of this, actually, you have to really do some kind of wall crossing like this. So
Do you think it's a special geometry of 3, 4, or it's a general?
yeah. I think it's geometry of threefolds. No, general tool. If you GIT gives you the general tool, but it's quite often doesn't work. And when you have to blow up this model and maybe contract something after this, in this case, we don't contract anything, then you really have to do something. Like, for example, if you have some nice way how you can describe some wall crossing, that it may help to change some polarization. But in our case, basically, we just got lucky, I think. So we... Okay.
So for example, now we have a GIT stability and a K stability.
Yeah.
I guess we have other kind of bounds of stability.
No, GIT stability is not canonical. It depends on your choice. For many varieties, for example, instead of this model, you can consider X as a complete intersection of degree 2, 0, 0, 2, and of degree 1, 1 in P3 cross P3. Basically, this is this break-in symmetry. You consider this not as P1 cross P1, as a quadric. And this is another quadric. And then you have absolutely different GIT problem, which may give you different answer. Like in our case, it's essentially give you this blow up in one point. But you can consider other GIT. So it's not a priori clear which one you should choose. When we start working on this problem, we was absolutely sure that the usual GIT, because it's so natural, it should be the right one, but it turned out to be not the case. So in many cases, and quite often in this case, it's okay, but quite often, Fano variety can be obtained, for example, as a blow up of something, but in different ways. You can blow up this or blow up that. And you can have different GIT, which give you absolutely different answer. So yeah, but K stability is canonical. You have no choice here.
Any further questions? Okay, so if not, let's send Benny again. Yeah, thank you very much.
Loginov, Kostya Loginov, my friend, he asked me, it would be nice ask physicists, because for physicists, they have physical meaning for this 4 qubits for quantum information. But maybe they would be interested in what's the physics meaning of this for them, because maybe it has a physics meaning, something like this. Yeah. Okay, good.